The universe began not with light, but with absolute darkness. Before the first stars even ignited, the cosmos may have been filled with black holes. These are not the kind born from dead stars. We are talking about primordial black holes, theoretical remnants from the universe's very first second of existence. In this exploration, you will discover 28 of the most fascinating and bizarre theories that suggest these ancient objects could be the key to cosmology's greatest puzzles. We will investigate if they are the invisible dark matter holding galaxies together, and whether one might be hiding in our own solar system right now. What single cosmic mystery do you most hope these primordial relics will solve? Gravity is the universe's great architect, yet it works with an invisible hand. We see its masterpiece in the graceful spin of galaxies, but the blueprint calls for far more material than we can ever see. This missing ingredient, dark matter, is the ghost in the cosmic machine, and one of the most compelling suspects is a swarm of ancient black holes. These would not be the stellar giants formed from collapsing stars. Instead, picture countless fragments of pure gravity, forged in the chaotic first moments of the Big Bang. Each one could be as small as an asteroid or as massive as a planet, drifting through the cosmos completely unseen. Their collective gravitational pull would be immense, weaving the invisible scaffold that keeps galaxies from flying apart. Imagine a trillion tiny anchors scattered through space, holding everything together with their silent, persistent weight. This idea elegantly solves a major puzzle because these primordial black holes interact with the universe through gravity alone. They do not emit light, they do not reflect it, they simply are, bending the fabric of space-time around them. The hunt for these phantom masses is on. Astronomers scan the skies for a phenomenon called microlensing, watching for moments when one of these dark objects passes in front of a distant star. Its gravity acts as a lens, briefly magnifying the star's light and betraying its invisible presence. Despite decades of searching without a definitive catch, this theory remains a favorite for its beautiful simplicity. It suggests that the very first structures born in the cosmos are also the hidden glue that binds it all together. But if dark matter is their modern role, where did these ancient objects actually come from? Their birth story is even more extreme than their current cosmic influence. The leading theory takes us back to the very beginning, to a fraction of a second after the Big Bang, during a period known as cosmic inflation. This was not an explosion in space, but a violent stretching of space itself, expanding faster than the speed of light. In that seething, energetic frenzy, the universe was not perfectly smooth. Think of a pot of water just as it begins to boil. Tiny bubbles of greater density would form and pop at random across the primordial soup. These were quantum fluctuations, minute wrinkles in the fabric of reality. Most of them smoothed themselves out instantly, but under the immense pressure and density of the infant cosmos, the largest of these wrinkles did not pop. Instead, they collapsed. When a region of space becomes dense enough, its own gravity becomes irresistible, pulling everything inward past a point of no return. In that single dramatic moment, a primordial black hole was born, not from a dying star, but from a direct knot of overheated spacetime. This origin story ties their existence directly to the most fundamental laws of physics. It means these black holes are not astronomical accidents, but cosmic fossils. They are preserved relics of the universe's most violent and energetic phase, carrying secrets about that initial expansion within their simple gravitational hearts. If we could study one directly, it would be like holding a tiny, frozen piece of the Big Bang itself. This cosmic imbalance is one of the most profound questions in all of science. Why does anything exist at all? The Big Bang should have created equal amounts of matter and antimatter, which would have immediately annihilated each other in a flash of pure energy, leaving behind a universe of light and nothing else. Yet here we are in a cosmos filled with galaxies, stars, and planets, all made of matter. Something must have tipped the scales. Remarkably, the answer might lie with those same primordial black holes. As they lose mass through a process called Hawking radiation, they do not simply vanish. They slowly evaporate, emitting a faint drizzle of particles back into the universe. The key theory suggests this evaporation was not symmetrical. It could have favored the creation of just a few more matter particles than antimatter particles for every billion that were destroyed. Think of a leaky faucet dripping into an empty bucket. If it drips just one extra drop of water for every million drops that evaporate over eons, the bucket will eventually fill. In the same way, over billions of years, the collective evaporation of countless primordial black holes could have slowly, patiently filled the universe with the excess matter that makes up everything we see. This process, known as baryogenesis, explains how a fundamental symmetry was broken, and these ancient black holes could have been the agents of that break. They are not just relics of the early universe. They could be the very reason the universe produced the material for stars, for planets, and for life itself. Without their subtle, preferential decay, the cosmos might have remained a perfect, empty void. The existence of our entire material world could be the long-lasting echo of their silent evaporation. If these black holes helped create all matter, they may have also built the universe's most imposing structures. At the heart of nearly every large galaxy, including our own Milky Way, sits a supermassive black hole, a gravitational monster weighing millions or even billions of times more than our Sun. How did these giants get so big, so fast in the early universe? One elegant solution points back to our ancient relics. A primordial black hole, perhaps the size of a star or larger, could have served as the perfect seed. In the chaotic nursery of a young galaxy, this dense kernel of gravity would naturally sink toward the center, its immense pull acting like a cosmic vacuum cleaner. It would start gobbling up vast clouds of gas, pulling in whole stars and merging with other black holes. With a ready-made head start, it could balloon in size at a staggering rate, quickly becoming the supermassive anchor we observe today. This theory neatly solves a major timing problem. Building such a behemoth from a single collapsing star seems to take too long, given how quickly we see them in the ancient cosmos. A primordial seed provides that crucial jump start. The competing idea suggests that a single stellar mass black hole could have grown large enough through accretion alone. But this process is messy and inefficient. As matter falls in, it heats up and radiates energy, which can actually push surrounding material away, starving the black hole and slowing its growth. Starting from a larger primordial seed bypasses this bottleneck, allowing for the rapid growth the early universe demands. The question remains, which path did nature take? Did these giants grow from the smallest beginnings, or were they planted as ready-made seeds in the cosmic dark? The answer lies locked within the event horizons of those ancient galactic cores. The very nature of a black hole is to consume, a one-way street into oblivion. But Stephen Hawking introduced a stunning paradox, suggesting that black holes are not entirely black. His revolutionary idea was that they can, in fact, radiate energy and slowly fade away. This process, Hawking radiation, arises from the strange quantum behavior at the very edge of the event horizon. According to quantum theory, empty space is not truly empty. It is a seething sea of virtual particles, pairs of matter and antimatter that constantly pop into existence and then annihilate each other almost instantly. Hawking realized that if this particle pair appears right at the boundary of a black hole, one particle could fall in while the other escapes. The escaping particle becomes real, carrying away a tiny bit of the black hole's mass. From a distance, it looks as if the black hole is glowing with a faint heat. For a giant black hole, this evaporation is so slow it is practically meaningless, a drop of water leaking from an ocean over trillions of years. But for the smallest primordial black holes, this is everything. Their tiny size means their Hawking radiation is much more intense. A primordial black hole with the mass of a small asteroid would have a lifetime shorter than the current age of the universe. As it nears the end of its life, the process accelerates dramatically. The black hole loses mass faster and faster, heating up until it unleashes its entire remaining energy in a final, violent burst. Think of a single firecracker popping in the vastness of space, but this one flash would contain the energy of millions of nuclear bombs, a concentrated blast of gamma rays and high-energy particles. This is the death cry of an ancient cosmic relic. Astronomers are actively searching the skies for these unique, unexplained flashes of energy, the potential signatures of primordial black holes breathing their last. Catching one of these final moments would be like witnessing the end of a universe that existed long before our own, a direct confirmation that the darkest objects in the cosmos can indeed flicker out of existence. That final, explosive death of a small black hole might be more than just a spectacular flash in the dark. It could be the source of some of the most powerful particles ever observed, cosmic bullets screaming across the universe at energies we can barely comprehend. These are ultra-high energy cosmic rays, atomic nuclei traveling at nearly the speed of light, constantly bombarding our atmosphere from deep space. Their origin is one of astrophysics' greatest puzzles, as no known object in the universe seems powerful enough to accelerate particles to such extreme velocities. One compelling theory points the finger directly at evaporating primordial black holes. When one of these ancient relics reaches the end of its life in a violent burst of Hawking radiation, it does not just release a flash of light. It unleashes a concentrated firestorm of fundamental particles. This includes gamma rays, but also protons, electrons, and even the elusive neutrinos, all spat out with unimaginable force. The mechanism is beautifully direct. Unlike a supernova or a pulsar that needs complex magnetic fields to accelerate particles, the evaporation of a black hole is a fundamental process of quantum gravity. The energy locked within its mass is converted directly into the kinetic energy of these escaping particles, granting them those staggering, ultra-high energies in one single quantum mechanical step. It is as if the black hole's entire existence is converted into a final, desperate shout made of matter and radiation. To test this idea, scientists have built enormous detectors that stare at the sky, not for light, but for the aftermath of these cosmic impacts. The Pierre Auger Observatory in Argentina, for instance, is a sprawling array of water tanks covering an area larger than a major city. When an ultra-high energy cosmic ray slams into our upper atmosphere, it creates a vast shower of secondary particles, a cascade that spreads out for miles. The observatory's tanks detect the faint ripple of this shower as it passes through, allowing physicists to trace the particle's energy and direction back to its source. The hunt is on for a specific pattern, a telltale signal that matches the unique particle mix predicted for a dying primordial black hole. Finding just one of these signatures would be a monumental discovery. It would solve two profound mysteries at once, revealing the origin of these ghostly cosmic rays and providing the first solid, indirect proof that the early universe was indeed teeming with these primordial gravitational fossils. Yet for all their cosmic influence, one of these primordial black holes might be far closer than we ever imagined. The outer reaches of our own solar system hold a gravitational mystery. Far beyond Neptune, a collection of icy objects follows elongated, tilted orbits that cluster together in a way that should not happen by chance. Something massive, perhaps 5 to 10 times the mass of Earth, seems to be herding them. Astronomers call this hypothetical object Planet 9. But what if it is not a planet at all? The culprit could be a primordial black hole, a relic from the dawn of time now trapped in our own cosmic backyard. This would be an object with the mass of a planet, yet compressed into a sphere smaller than a baseball. It would be utterly black, emitting no light, a ghost in the orbital machinery of our solar system. Its presence would be felt only through its immense gravitational pull, perfectly explaining the strange paths of those distant ice worlds as they swing around the sun. How could we ever hope to spot such a perfect cloak of darkness? The answer lies in the subtle ways it would interact with its environment. As this black hole moves through the cloud of comets and debris in the outer solar system, its gravity would occasionally tear apart a passing icy body. The resulting debris, falling towards the unseen object, would heat up through friction and collision, creating a faint, flickering glow of X-rays or other radiation. These would be accretion flares, brief signals of destruction pointing to an invisible source. An even more promising method is micro-lensing. If this black hole were to pass directly in front of a distant background star, its gravity would act as a magnifying glass. For a few moments, the star would appear to brighten dramatically before fading back to normal. Our telescopes are now powerful enough to scan the vast outer darkness for these tiny, telltale flashes of light. Projects like the Legacy Survey of Space and Time at the Vera C. Rubin Observatory are designed to map the sky with incredible precision, and they could be the key to finding this phantom neighbor. The hunt is not for a new world, but for the gravitational shadow of a cosmic fossil. Confirming its existence would fundamentally reshape our understanding of the solar system, revealing that we share our celestial neighborhood with a primordial remnant from the universe's very first second. While Planet 9 remains a speculative neighbor, we must journey back to the universe's infancy to find another dramatic origin story for these objects. Picture the cosmos not as a smooth, expanding fireball, but as a pot of water coming to a rolling boil. This was the era of first-order phase transitions, a fundamental shift in the fabric of reality itself. In its earliest, hottest moments, the universe was filled with a unified field of energy, a single state of being. As it expanded and cooled, this field underwent a radical transformation, much like steam condensing into water or water freezing into ice. But this was not a gentle, uniform process. It happened in a violent, chaotic cascade. Bubbles of the new, more stable vacuum began to spontaneously form and expand at nearly the speed of light. These bubbles were not empty. They were domains of a new reality, pushing against the old, high-energy state that still surrounded them. Now, imagine the incredible energy released when these bubbles collided and merged. The walls of these expanding domains slammed into each other with unimaginable force. At these collision points, space itself became wrinkled and concentrated, creating regions of such immense density that they could directly collapse into black holes. It was not a slow accumulation of matter, but a sudden, catastrophic implosion born from the raw energy of cosmic change. This violent, bubbling process offers a distinct advantage for theorists. The size of the bubbles and the energy of the collisions would naturally produce primordial black holes within a specific range of masses. Unlike the random distribution from inflation, a phase transition could have preferentially created black holes of a certain size, perhaps all with masses similar to a large asteroid or even a small planet. This gives astronomers a clearer target to look for, a specific fingerprint in the mass spectrum of dark matter. The death cries of these particular black holes, or their collective gravitational pull, would carry the signature of that ancient, universe-altering boil. Finding that signal would do more than just confirm their existence. It would provide a direct window into the forces and symmetries that defined reality in its first fleeting moments, revealing a cosmos forged in the violent clash of bubbling vacuums. Sound carries a hidden signature of creation. The early universe was not a silent void, but a seething ocean of hot, dense plasma, ringing with powerful sound waves. These were not ordinary sounds, but pressure waves born from the initial violence of the Big Bang, rippling through the primordial soup at over half the speed of light. As these waves traveled, they created a predictable pattern like ripples from a stone thrown into a pond. Regions where the waves peaked became incredibly dense, packed with matter and energy, while the troughs between them were far more sparse. In the universe's first second, these peaks were so extreme, so unimaginably dense, that they could have crossed a critical threshold. Their own gravity would have become overwhelming, causing them to collapse directly into knots of space-time. These are the primordial black holes, formed not from silent quantum fluctuations, but from the resonant peaks of the universe's first and most powerful song. This theory ties their birth directly to the acoustic fingerprint of the cosmos, a fingerprint we can still observe today in the faint afterglow of the Big Bang, the cosmic microwave background. This relic light shows us the faint imprint of those ancient density waves, frozen in time when the universe was only 380,000 years old. The specific pattern of hot and cold spots on this cosmic background is a direct map of those sound wave peaks and troughs. By studying this map with incredible precision, cosmologists can search for the subtle signs that the densest peaks went on to form black holes. The future of this search, however, may not rely on light at all, but on listening for the vibrations of space-time itself. When those dense regions collapsed, the event would have sent powerful gravitational waves rippling across the cosmos. These are not sound waves, but literal vibrations in the fabric of reality. Next-generation observatories like the Space-Based Laser Interferometer Space Antenna, or LISA, are being designed to listen for these specific high-frequency ripples from the very early universe. Detecting a chorus of these ancient gravitational waves would be like hearing the echoes of those first sonic booms, confirming that the densest notes in the cosmos's opening chord truly did give birth to shadows that have lasted until today. The silent hunt for these cosmic phantoms became a real scientific mission in the 1990s. Astronomers launched an ambitious project named MACHO, an acronym for Massive Compact Halo Object. Their target was the vast halo of our Milky Way galaxy, the very place where dark matter was thought to be concentrated. If primordial black holes made up this invisible mass, they would be drifting everywhere, and their gravity offered a perfect way to spot them. The method was gravitational microlensing. Imagine a single, invisible primordial black hole, perhaps with the mass of Jupiter, drifting through the dark halo. By sheer chance, its path could carry it directly in front of a star in a neighboring galaxy, like the Large Magellanic Cloud. As the black hole passes in front of the star, its gravity acts as a tiny lens, bending and focusing the starlight toward Earth. For a few days or weeks, that distant star would appear to brighten dramatically, then slowly fade back to its normal luminosity. It would be a perfectly symmetrical light curve, a telltale signature of an invisible object magnifying the light. The MACHO project and its counterparts spent years staring at millions of stars, waiting for these elusive flashes. They did see a handful of candidate events, moments where a star brightened in just the right way. But there were not enough of them. The results were definitive yet disappointing. The data ruled out the possibility that all the dark matter in our galaxy's halo could be made of primordial black holes within a specific mass range. If they were as common as stars or as small as asteroids, the sky would have been flickering with these microlensing events constantly. The silence was profound. It meant that primordial black holes could not be the sole answer to the dark matter puzzle, at least not in the simplest form of the theory. This null result was not a failure but a crucial step. It narrowed the search dramatically, telling physicists that if these ancient black holes do make up the dark matter, they must exist in a very specific window of mass, either much smaller or vastly larger than the objects MACHO was designed to find. The hunt had to evolve, moving from a search for a dominant population to a quest for a more elusive, specialized breed of cosmic fossil. Our universe may be crisscrossed by cosmic scars. These are not physical marks, but hypothetical flaws in the fabric of spacetime itself, known as cosmic strings. Think of the universe cooling from its initial hot, symmetrical state. As it transitions, the fabric of reality can develop defects, much like cracks forming in ice as water freezes. A cosmic string is an incredibly dense, one-dimensional crack, a flaw in the vacuum of space. It is not made of matter, but of pure energy, a thread of space-time under immense tension. A single string thinner than a proton could be so heavy that a mile of it would outweigh Mount Everest. When these unimaginably dense strings move through the cosmos, they can vibrate, snap, and most importantly, collide with one another. The theory suggests that when two such strings cross or a loop of string collapses, the event is catastrophic. The immense energy bound up in these defects must go somewhere, and in that instant of collision or collapse, it is released in a violent, concentrated knot. This knot of energy becomes so dense that its own gravity takes over, and it collapses directly into a primordial black hole. This process is beautifully mechanical. Unlike the random fluctuations of inflation or the resonant peaks of sound waves, cosmic strings offer a precise factory. The size of the black hole produced depends directly on the properties of the string itself, its tension, and the size of the loop that collapses. This means cosmic strings could have produced primordial black holes across a vast spectrum of masses, from microscopic specks to objects larger than stars, all from the same fundamental mechanism. The collisions of these cosmic scars would have sown the early universe with gravitational seeds, each one a silent remnant of a time when space-time itself was crystallizing into the reality we know today. The cosmos has a chemical mystery etched in its oldest stars. The first few minutes after the Big Bang were a frantic forge, a period called Big Bang nucleosynthesis that fused the universe's original hydrogen and helium. The equations predict a certain amount of a light metal, lithium-7, should have been created and then frozen into the first stars. Yet when we look at these ancient stellar relics, the amount of lithium we measure is consistently lower, only about a third of what the models say should be there. Something must have destroyed a large portion of the primordial lithium after it was made. The culprit might have been the smallest and most fleeting of all primordial black holes. In their final, furious moments of evaporation, these tiny black holes would have unleashed a storm of high-energy particles and radiation. This was not a gentle rain, but a violent hailstorm of protons, electrons, and antimatter sleeting through the infant cosmos. This barrage of energy would have slammed into the newly forged nuclei of lithium-7. Think of a perfectly stacked pyramid of marbles. A single high-energy particle from a dying black hole could act like a precisely thrown stone, striking that lithium nucleus and shattering it apart, breaking it down into smaller, more stable atoms like helium. This process, known as spallation, effectively erased a portion of the universe's initial lithium supply. It is an incredibly elegant solution. The very objects that may have helped create the matter excess through their decay also acted as cosmic editors, fine-tuning the chemical composition of the universe by selectively destroying one specific element. This theory provides a direct, testable link between the quantum gravitational death of a black hole and the observable chemistry of the oldest stars in our galaxy. If correct, the lithium deficit is not a flaw in our understanding of the Big Bang, but rather a fossilized record of a long-vanished population of tiny, evaporating black holes, their final breaths literally sculpting the elemental landscape we see today. The silent death of a black hole is one thing, but the violent dance of two of them is another story entirely. Picture a pair of primordial black holes, born close together in the universe's first second, locked in a mutual gravitational embrace. For billions of years, they orbit each other in the darkness, a slow, cosmic waltz that gradually saps their orbital energy. That lost energy has to go somewhere, and it radiates outward as ripples in the very fabric of spacetime itself. These are gravitational waves, and a binary pair of primordial black holes would be a prolific, constant source of them. For most of cosmic history, this signal would have been a faint whisper, lost in the background hum of the universe. But in their final moments, as their orbits tighten and they spiral inward at a significant fraction of the speed of light, that whisper becomes a deafening cosmic shout. This is the moment observatories like LIGO and Virgo are built to hear, when their lasers detected the first gravitational waves in 2015. It was from the merger of two stellar mass black holes. It confirmed a monumental prediction of Einstein's theory, but a key question remained. Were those black holes the remains of dead stars, or were they something much, much older? The properties of the merger can hold the answer. Primordial black holes would likely have distinct characteristics. First, their masses could be unusual. Stellar evolution has natural limits, making black holes heavier than about 50 solar masses quite rare. If we consistently detect mergers involving black holes far heavier than that, it points to an origin that bypasses stars entirely. Second, consider their spin. Black holes born from collapsing stars often have a significant spin, a relic of the angular momentum of their parent star. But primordial black holes formed from the direct collapse of dense regions could have very little spin. They would be like perfect, non-rotating spheres of darkness. When LIGO and Virgo record a merger, they are not just hearing a thump. They are listening to a complex chirp that encodes the masses, spins, and orbits of the colliding objects. A pattern of events with unexpectedly high masses and low spins would be a powerful fingerprint pointing directly to a primordial origin. Each such detection would be more than just the discovery of a new black hole. It would be a direct message from the first moments of time, a vibration sent across 13.8 billion years, finally arriving at our detectors to tell us how the universe began. The perfect blackness of a black hole presents physics with its most troubling paradox. For decades, Stephen Hawking argued that anything falling past the event horizon is lost forever, its information irretrievably scrambled into random thermal radiation. This idea that the universe could simply forget violates a fundamental tenet of quantum mechanics, which states that information can never be truly destroyed. The conflict is known as the black hole information paradox, and its resolution might lie in a radical new idea called quantum hair. This theory suggests that primordial black holes are not the perfectly smooth, featureless objects of classical physics. They are not bald. Instead, the quantum information of everything they have ever consumed is not lost inside their depths, but is somehow imprinted on their event horizons in subtle, complex structures. Think of it like a hologram where all the data of a three-dimensional object is encoded on a two-dimensional surface. The event horizon becomes a vast quantum hard drive, storing the history of every particle that has crossed its threshold. These imprints are the black hole's quantum hair, faint topological features that whisper the story of its past. For a primordial black hole which has consumed only the pristine matter of the early universe, this hair would be incredibly simple, a clean record of its initial formation. Detecting this effect directly is a monumental challenge, but it offers a new way to search for these ancient objects. The presence of quantum hair would subtly alter how a black hole interacts with its environment, perhaps changing the way it gravitationally lenses light or how it merges with another black hole. If we could observe the gravitational wave signal from two merging primordial black holes with exquisite precision, the specific ring-down after their collision might carry the signature of this quantum structure, a faint echo of the information preserved on their surfaces. Solving the information paradox would be a revolution in our understanding of reality, and these primordial black holes, as the simplest and oldest of their kind, could be the perfect laboratories to finally prove that the universe never, ever forgets. The fabric of our universe might be stitched together with the remnants of others. This idea ventures beyond the Big Bang into the speculative realm of the multiverse, where primordial black holes take on an even more profound identity. They might not be objects within our universe at all, but rather cosmic orphans, artifacts from collisions with other universes entirely. In this breathtaking scenario, a primordial black hole could be a baby universe in its own right, a tiny pocket of space-time that pinched off from a larger parent cosmos, now existing within our own as a simple sphere of gravity. Alternatively, picture our universe as a single bubble in a vast, frothing cosmic foam, constantly jostling against its neighbors. When two such bubbles make contact, the collision would release an unimaginable concentration of energy, a shockwave so intense it could instantly forge a black hole at the point of impact. This formation mechanism is fundamentally different from anything happening inside a single, isolated universe. A chaotic multiverse landscape acts like a cosmic factory, capable of producing a staggering variety of black holes. In our universe alone, the mass range for these objects is constrained by the specific conditions of our Big Bang and the laws of physics as we know them. But in a multiverse, those initial conditions and even the fundamental constants could be different in every single bubble. One collision might produce a black hole with the mass of a mountain, while another creates a monster heavier than 1,000 suns. The resulting population would be incredibly diverse, a menagerie of gravitational relics with properties far beyond what a single universe could ever create. This could explain why our searches for a single, neat population of primordial black holes have been so challenging. We are not looking for one type of object, but for a chaotic collection of cosmic immigrants, each with its own unique origin story. Their gravitational fingerprints, their Hawking radiation signatures, and even their distribution throughout space would carry the indelible mark of a reality far grander and more complex than we ever imagined. Finding one of these multiversal artifacts would be the first tangible evidence that our cosmos is just one page in an infinite book. Deep in the cosmos, brilliant flashes of radio energy erupt and vanish in less than a blink of an eye. These fast radio bursts are one of astronomy's most persistent puzzles, and their explanation might be tied to the gravity of the ancient past. One theory suggests these fleeting, high-energy events could be the death cries of the smallest primordial black holes. As a microscopic black hole nears the end of its evaporation, it could potentially develop a powerful magnetic field in its final, frantic moments. When it finally explodes, that magnetic field collapses, and its energy is violently transferred into a focused beam of radio waves, a single, brilliant flash visible across the universe. Another, even more dramatic mechanism involves a primordial black hole on a collision course. Imagine one of these ancient specks of gravity, smaller than an atom but with the mass of a mountain, slamming directly into a neutron star. The impact would be catastrophic. It would not swallow the star whole, but its immense gravity would send powerful shockwaves rippling through the star's incredibly rigid crust. This would trigger a starquake, a seismic event of cosmic proportions, releasing a colossal burst of magnetic energy that we would observe as a fast radio burst. This idea creatively links two profound mysteries. Of course, there are significant challenges. The timing has to be perfect, and the physics of such an interaction is incredibly complex. Yet the sheer ingenuity is compelling. It proposes that the solution to a modern astronomical enigma might lie in the violent interaction between the densest objects we know and the oldest. Each unexplained flash of radio light could be a signal, a final message from a primordial black hole meeting its end, or a cosmic collision spanning the entirety of cosmic history. Gravity's invisible architects may have left their blueprints in the faintest galaxies. If dark matter is indeed a vast population of primordial black holes, their collective mass would do more than just provide the gravitational glue holding galaxies together. It would actively sculpt their very architecture from the inside out. Picture the formation of a galaxy not as a smooth accumulation of gas, but as a dynamic dance where countless invisible knots of gravity pull and tug on the visible material. These primordial black holes would sink to the center of the galaxy's dark matter halo, their sheer numbers creating a powerful, concentrated gravitational well. This dense, invisible core would act like a cosmic anchor, dictating how stars and gas clouds move. In large spiral galaxies like our Milky Way, this could result in a much sharper rise in the rotation speed of stars closer to the galactic center, a subtle signature etched into the motions of billions of suns. But the most telling clues might be found in the universe's smallest and most pristine galaxies, the dwarfs. These fragile collections of stars are so dominated by dark matter that they are essentially cosmic laboratories for studying its nature. A swarm of primordial black holes would leave a distinct mark here. Because they are discrete, solid objects, their gravitational influence would be slightly grainy compared to a perfectly smooth cloud of dark matter particles. This graininess could prevent the dark matter from collapsing into an extremely dense, cuspy center, instead resulting in a more spread-out, core-like profile. Astronomers are actively debating the inner structures of these dwarf galaxies, searching for exactly this kind of fingerprint. Now, contrast this with the primary alternative, WIMP, or weakly interacting massive particles. WIMP are hypothetical subatomic particles that essentially form a continuous, fluid-like sea of dark matter. Their interactions are so feeble that they would create an incredibly smooth and predictable gravitational field, leading to different predictions for the density at the very heart of a dwarf galaxy. The ONG Chinese letter of these faint stellar systems is in essence a competition between these two ideas. Is the dark matter halo of a galaxy a smooth ocean, or is it a shimmering swarm of ancient gravitational specks? The answer is written in the slow, orbital dance of stars on the cosmic periphery, a dance directed by shadows from the dawn of time. Supersymmetry proposes that every particle we know has a hidden, super-powered twin. This elegant theory extends the standard model of particle physics, aiming to solve some of its deepest puzzles, like the nature of dark matter. For every electron, there should be a selectron. For every quark, a squark. These superpartners are predicted to be far heavier than their ordinary counterparts, and in the universe's first instance, they would have been incredibly abundant. As the cosmos expanded and cooled, these heavy, unstable particles began to decay, vanishing out of existence in a flood of energy. But this decay was not always smooth or uniform. In some regions, a dense concentration of these superpartners might have decayed all at once. The sudden, simultaneous release of their energy would have flooded a local patch of space, creating an immense temporary spike in density. Think of a field of dried leaves. If you light one leaf, it smolders and goes out. But if you pile them high and light the stack, you get a roaring, concentrated bonfire. In the same way, the collective decay of a cluster of supersymmetric particles would have created a bonfire of energy so intense that the region's own gravity became overwhelming. This ultra-dense pocket would then collapse directly into a primordial black hole. This formation mechanism is profoundly different from others. It directly ties the existence of these gravitational fossils to the realm of particle physics. We have yet to find any evidence for supersymmetry in our most powerful particle colliders, which has been a disappointment for many physicists. But what if we have been looking in the wrong place? The signature of these superparticles might not be in a detector on Earth, but written in the gravitational architecture of the entire cosmos. If a specific population of primordial black holes is ever discovered, with a mass distribution that perfectly matches predictions from supersymmetric decay, it would be a monumental achievement. It would mean we tested a fundamental theory of particle physics, not by smashing protons together, but by observing the ancient shadows they cast upon the universe. The failure to find supersymmetry in the lab would be completely overturned by a successful observation in the sky, proving that the particles were there all along, shaping the universe in its first fleeting moments. The silent death of a black hole is one thing, but the violent dance of two of them is another story entirely. Picture a pair of primordial black holes born close together in the universe's first second, locked in a mutual gravitational embrace. For billions of years, they orbit each other in the darkness, a slow, cosmic waltz that gradually saps their orbital energy. That lost energy has to go somewhere, and it radiates outward as ripples in the very fabric of spacetime itself. These are gravitational waves, and a binary pair of primordial black holes would be a prolific, constant source of them. For most of cosmic history, this signal would have been a faint whisper, lost in the background hum of the universe. But in their final moments, as their orbits tighten and they spiral inward at a significant fraction of the speed of light, that whisper becomes a deafening cosmic shout. This is the moment observatories like LIGO and Virgo are built to hear. When their lasers detected the first gravitational waves in 2015, it was from the merger of two stellar mass black holes. It confirmed a monumental prediction of Einstein's theory, but a key question remained. Were those black holes the remains of dead stars, or were they something much, much older? The properties of the merger can hold the answer. Primordial black holes would likely have distinct characteristics. First, their masses could be unusual. Stellar evolution has natural limits, making black holes heavier than about 50 solar masses quite rare. If we consistently detect mergers involving black holes far heavier than that, it points to an origin that bypasses stars entirely. Second, consider their spin. Black holes born from collapsing stars often have a significant spin, a relic of the angular momentum of their parent star. But primordial black holes formed from the direct collapse of dense regions could have very little spin. They would be like perfect, non-rotating spheres of darkness. When LIGO and Virgo record a merger, they are not just hearing a thump. They are listening to a complex chirp that encodes the masses, spins, and orbits of the colliding objects. A pattern of events with unexpectedly high masses and low spins would be a powerful fingerprint pointing directly to a primordial origin. Each such detection would be more than just the discovery of a new black hole. It would be a direct message from the first moments of time, a vibration sent across 13.8 billion years, finally arriving at our detectors to tell us how the universe began. The faint afterglow of the Big Bang holds a frozen picture of the infant cosmos, and primordial black holes may have scribbled their signature across it. This cosmic microwave background radiation is our deepest view back in time, and the gravity or radiation from these ancient objects could have altered its subtle patterns. One way involves their insatiable appetite. In the era before the first stars, even a small primordial black hole would have been a voracious eater, pulling in the surrounding hydrogen gas. As this gas spiraled inward, it would have compressed and heated to extreme temperatures, causing it to glow with high-energy radiation. This radiation, flooding the early universe, would have battered into other hydrogen atoms, stripping away their electrons in a process called ionization. This re-ionization of the primordial gas would have left a specific, patchy imprint on the polarization of the cosmic microwave background, a telltale sign of early energy sources that standard models struggle to explain. The second mechanism is even more direct, a purely gravitational fingerprint. A vast population of primordial black holes drifting through the early universe would have subtly warped the fabric of space-time around them. As the light of the cosmic microwave background traveled for billions of years to reach us, it would have passed through this uneven gravitational landscape. The black holes would have acted as tiny lenses, minutely distorting the light's path and creating specific, statistical irregularities in the temperature map we observe today. It is like looking at a reflection on the surface of a pond that is being gently disturbed by countless unseen pebbles. The pattern of ripples betrays the presence of the objects beneath the surface. By comparing the exquisitely detailed maps from observatories like the Planck satellite against predictions from these two effects, cosmologists can place incredibly tight constraints on how many primordial black holes could have existed. So far, the cosmic background appears remarkably smooth, suggesting they cannot be the dominant form of dark matter. Yet, the hunt continues for a subtler signal, a faint ghost in the oldest light we can see, waiting to be discovered. The quest to unite gravity with the quantum world is the single greatest challenge in modern physics. Primordial black holes could be the key that finally unlocks this mystery. Our two most successful theories, general relativity and quantum mechanics, describe the universe with breathtaking accuracy, but they speak entirely different languages. One paints a smooth, geometric picture of spacetime, while the other reveals a fuzzy, probabilistic world of chance. They clash violently at the center of a black hole, a point of infinite density known as a singularity, where the laws of physics as we know them simply break down. But the smallest primordial black holes offer a way out of this impasse. Because of their tiny size, the physics governing their entire life cycle, from explosive birth to final evaporation, operates at the unimaginably high energy scales where these two theories must finally merge into a single coherent framework, a theory of quantum gravity. Observing such an object would be like finding a fossil from the very frontier of physics itself. Its behavior would be dictated not by Einstein's equations alone, but by the quantum nature of spacetime. What does that even look like? Picture spacetime not as a smooth, continuous fabric, but as a seething foam of tiny, discrete loops and twists, a pixelated reality at the smallest possible scale. This is the prediction of leading theories like loop quantum gravity. A microscopic primordial black hole would be so small that it would be constantly interacting with this frothy, quantum texture of reality. Its evaporation through Hawking radiation would not be a perfectly smooth process, but would carry subtle imprints of this underlying graininess. The specific spectrum of particles it emits in its final moments, the precise timing of its explosive death, these details would be a direct signal from the quantum gravitational realm. For the first time, we would have empirical data from a regime that our particle colliders can never hope to reach. It would tell us if spacetime is truly made of loops, strings, or some other fundamental building block we have yet to conceive. A primordial black hole is more than a cosmic relic. It is a natural laboratory, a gift from the universe's first instant that allows us to probe the deepest questions of existence without ever building a machine. Finding one would not just solve an astronomical puzzle, it would hand us the first chapter of the ultimate rulebook for reality. The quiet decay of a lone black hole is one thing, but a direct collision with a stellar corpse unleashes pure cosmic chaos. Among the most dramatic theories is the idea of a primordial black hole acting as a trigger for exotic, universe-shaking explosions. Picture a scenario where one of these ancient specks, perhaps with the mass of a mountain but no wider than an atom, is on a direct intercept course with a neutron star. This is no gentle merger. The neutron star is a perfect sphere of ultra-dense matter, so compact that a single teaspoon of it would weigh billions of tons. The tiny black hole slams into this incredibly rigid object, and because it is so dense, simply punches straight through the outer crust, plunging into the star's interior. It does not stop there. Now buried deep inside the neutron star, the black hole begins to feed. Its immense gravity starts pulling the surrounding neutron-rich material directly into its event horizon. This initiates a runaway process, a chain reaction of accretion. The black hole gorges itself, growing in mass and pulling in material faster and faster from the inside out. Within a matter of hours or days, it consumes the entire neutron star from the inside. The result is a cataclysmic release of energy, a titanic explosion that could outshine a galaxy for a brief, brilliant moment. To astronomers, this event would likely manifest as a short gamma-ray burst, one of the most powerful explosions known. The entire neutron star is converted into a firestorm of radiation and gravitational waves, a flashpoint of destruction born from a collision of the ancient and the dead. A similar, though slightly less violent, fate could await a white dwarf star. If a primordial black hole were to collide with this aging stellar cinder, the process would be different but no less spectacular. The black hole would sink to the white dwarf center and begin accreting its carbon and oxygen fuel. This sudden, intense heating at the very heart of the star could ignite a runaway thermonuclear fusion reaction. Instead of a slow burn, the entire white dwarf would detonate in an instant, mimicking a Type Ia supernova. This is a stellar explosion so standardized that astronomers use it as a cosmic measuring tape to gauge the expansion of the universe. The implications are staggering. It suggests that some of the key markers we use to understand the cosmos might themselves be triggered by these invisible primordial seeds. A single microscopic object from the beginning of time could, billions of years later, impersonate the death of a star, its gravitational touch lighting a fuse that reshapes our view of the heavens. These cosmic vibrations find a more intricate rhythm in the behavior of invisible fields that permeate all of reality. To understand this, picture a perfectly still, silent drumhead stretched across the universe. This drumhead is a scalar field, a fundamental energy field similar to the one that gives particles their mass. As the violent expansion of inflation ended, this field was jolted like a drumhead struck by a mallet. It began to oscillate, vibrating up and down in a complex rhythmic pattern. But this cosmic drumhead was not perfectly uniform. Just as a real drumskin can develop standing waves that cause certain spots to vibrate more intensely than others, the scalar field began to fragment. Regions of higher energy density began to pull themselves together, resisting the smoothing effect of expansion. These clumps of concentrated field energy are known as oscillons, or in some theories, cue balls. They are not made of matter, but of pure, self-sustaining vibration, like a single, persistent note held in one spot on the drum. The key to their story is stability. Most vibrations would quickly dissipate, but these oscillons were remarkably long-lived, acting as temporary reservoirs of immense energy density. They were knots of potential, holding their shape against the pull of the expanding universe. And in the extreme conditions of the early cosmos, that was enough. If an oscillon became sufficiently dense, its own self-gravity would eventually win out. The vibrating knot of energy would cross a critical threshold and collapse, not into a star or a planet, but directly into a primordial black hole. This formation path is beautifully different from random quantum fluctuations. It is a structured, resonant process where the specific properties of the scalar field dictate the mass and abundance of the black holes produced. The universe was not just boiling chaotically, it was ringing like a bell, and the loudest, most persistent notes condensed into permanent gravitational shadows. Finding a population of primordial black holes with a very specific, narrow range of masses could be the direct echo of that first cosmic chord. Another cosmic puzzle piece might fit perfectly into this gravitational picture. The action is a hypothetical particle so light and elusive it could drift through a planet as if it were empty space, and it is a leading candidate for the other half of the dark matter mystery. But what if these two contenders, primordial black holes and actions, are not rivals at all but cosmic partners? A fascinating theory suggests they could be deeply intertwined, each making the other easier to find. One version of this idea begins with a newly formed primordial black hole. Its intense gravitational field could have acted like a powerful magnet, pulling in a vast, diffuse cloud of actions from the surrounding early universe. This would create a dense, swirling halo around the black hole, a cocoon of invisible particles bound by its gravity. This action cloud would not be static. It would oscillate, generating its own subtle gravitational waves, a faint, continuous hum that could be detectable by future observatories. This symbiotic relationship offers a brilliant detection strategy. A lone, stellar mass black hole drifting in empty space is nearly impossible to spot. But if it is shrouded in a massive action cloud, the entire system has a much larger gravitational footprint, making it a far more visible target for our instruments. The other side of this partnership is even more explosive. When a small primordial black hole nears the end of its life through Hawking radiation, its final, violent evaporation could produce a spectacular burst of actions alongside the usual particles. This sudden, dense outpouring of these elusive particles would be a unique cosmic signal. While we cannot detect individual actions easily, such a concentrated burst could have subtle collective effects, perhaps leaving a distinct imprint on the background radiation of the universe or influencing the magnetic fields of galaxies. This partnership elegantly solves multiple problems at once. It provides a mechanism to create dense clumps of action dark matter, something that is otherwise difficult to explain. It also gives us new ways to hunt for both entities, turning the search for one invisible component of the cosmos into a hunt for a coupled system. The silence in our current searches may not mean these things do not exist, but that we have been listening for a solo performance when we should have been waiting for a cosmic duet. A primordial black hole is more than a gravitational trap. It is a perfect cosmic vault. Every detail about it, from its mass to its rotation, is a frozen record of the exact moment it was born. This relic does not just exist from the early universe, it actively preserves a snapshot of its birth environment. The mass of a primordial black hole tells a precise story. It reveals the density of the specific patch of space that collapsed to form it. A heavier black hole means the region was incredibly dense, a sharp peak in the primordial soup. A lighter one suggests a more moderate wrinkle in space-time. Their collective distribution across the cosmos is a statistical map of those initial conditions, a census of the universe's first structures. Even the spin of a primordial black hole is a direct fossil. If it formed from a region that was not perfectly smooth, but had some slight internal turbulence or rotation, that motion would have been amplified during the collapse, imprinting a specific spin onto the newborn object. A black hole with no spin at all points to a perfectly calm and symmetrical birth, while one with rapid rotation whispers of violent, swirling chaos in its first microsecond of life. Finding and studying one of these objects would be the ultimate archaeological dig. It would be like unearthing a sealed vessel from a forgotten civilization, but this vessel was forged in the first second of creation. Inside is not pottery or tools, but the fundamental parameters of reality itself, the temperature, the pressure, and the very rules of physics as they existed at the dawn of time. We would hold in our hands, through our telescopes and detectors, a direct piece of evidence from a moment otherwise lost forever to the expansion of the cosmos. The most stable form of matter in the universe might not be the atoms we know, but something far stranger. Deep within this speculative theory lies the idea that some primordial black holes are not black holes at all. They could be cosmic imposters, dense nuggets of an exotic substance known as strange quark matter. To understand this, we must descend into the heart of a neutron star. Under the immense gravitational pressure there, the protons and electrons that make up normal matter are crushed together, dissolving into a soup of their fundamental components, quarks. This creates an ultra-dense sea of up and down quarks, but physicists theorize that under even more extreme conditions, a third type of quark, the strange quark, could join the party. This new mixture, strange quark matter, is predicted to be phenomenally stable, perhaps the most stable configuration of matter possible. A single chunk of this stuff would be a perfect, indestructible crystal of pure nuclear force. The most radical property of strange matter is its scaling. While a normal atomic nucleus becomes unstable if it gets too large, a lump of strange quark matter is thought to be stable at any size. A piece with the mass of a mountain or the mass of a planet would be equally viable, a single, gigantic atom held together by the strong nuclear force. From the outside, such an object would be virtually indistinguishable from a true black hole of the same mass. It would be completely dark, with an unimaginably strong gravitational pull, warping space-time around it just like its gravitational cousin. The only way to tell them apart would be to get impossibly close. A true primordial black hole has an event horizon, a point of no return. A strange matter nugget, however, would have a solid surface. If you could somehow approach it without being torn apart by gravity, you would eventually hit a physical wall, the hardest surface in the entire cosmos. The origin story for these objects is as wild as they are. They might not have formed in the smooth expansion of the early universe, but in the shattering collisions between neutron stars. A cataclysmic impact could have splattered droplets of this strange matter out into the cosmos, where they cooled and drifted for eons. These exotic nuggets would then masquerade as primordial black holes, fooling our telescopes and gravitational wave detectors. Finding one would mean discovering an entirely new state of existence, a perfect alien substance that has been hiding in plain sight since the beginning of time. That final, silent evaporation presents physics with its most profound philosophical crisis. Stephen Hawking's own discovery, the radiation that bears his name, led directly to the black hole information paradox. The problem is devastatingly simple. Quantum mechanics, the rulebook for the universe, states that information can never be destroyed. Every particle that falls into a black hole carries information about its properties, its spin, its charge. If the black hole eventually evaporates completely, leaving behind only a featureless puff of Hawking radiation, what happened to all that information? It seems to have been erased from reality, a clear violation of a fundamental cosmic law. One radical solution suggests the event horizon is not the gentle boundary we imagine. Instead, it could be a firewall, a blistering wall of high-energy particles that instantly incinerates anything crossing it, preserving information at the boundary by destroying the infalling object entirely. Another, more elegant idea is the holographic principle. It proposes that all the information about what falls into a three-dimensional black hole is not lost inside, but is perfectly encoded on its two-dimensional event horizon like a complex hologram. The evaporation process would then be a slow, meticulous decoding of that information, imprinted onto the escaping radiation. To us, that radiation looks random and thermal, but in theory, it contains the entire history of the black hole in its subtle correlations. This is where primordial black holes become the ultimate testing ground. Their entire life cycle, from formation to complete evaporation, could happen within the age of the universe. If we could ever detect one in its final moments, the precise spectrum and pattern of its death-throw radiation would be the ultimate data set. A smooth, thermal spectrum would suggest information is truly lost, upending our understanding of physics. But a spectrum with subtle, complex patterns would be the smoking gun, proof that information is preserved, scrambled onto the Hawking radiation like a cosmic cipher. Observing this would not just confirm a theory, it would reveal the deepest nature of reality, showing us whether the universe is truly a machine that never forgets. Our search for these cosmic ghosts is now a global, multi-pronged scientific campaign. We are no longer just theorizing, we are actively hunting, using every tool at our disposal to find a primordial black hole. Gravitational wave observatories like LIGO, Virgo, and the future space-based LISA mission are listening for the faint whispers of their mergers, the subtle chirps that could reveal a primordial origin through their unique masses and spins. Simultaneously, powerful optical telescopes, particularly the Vera C. Rubin Observatory, are beginning epic microlensing surveys. They will scan billions of stars for the telltale, symmetrical brightening that betrays an invisible object passing in front of them, a direct detection of a dark mass drifting through the galactic halo. In space, gamma-ray telescopes are on high alert, their instruments tuned to catch the final, explosive death cries of the smallest black holes as they evaporate in a flash of high-energy radiation. And the search comes even closer to home. There are serious proposals for missions that would scan the outer solar system for tiny, fleeting optical flashes. What could cause such a flash? The impact of a small, asteroid-mass primordial black hole striking a distant, icy body. The resulting debris cloud, heated to incandescence, would be a brief but brilliant signal pointing directly to our phantom neighbor. We are in a golden age of astronomical discovery, a time when the tools to find these ancient relics are either here or on the near horizon. The combined power of these observatories, each listening for a different signature, means the first definitive proof of a primordial black hole could be announced tomorrow. After decades of searching in the dark, we are finally bringing the light of modern science to bear on the shadows of the ancient cosmos. From the cosmic dawn to our own solar backyard, these 28 theories paint a breathtaking portrait of possibility. Primordial black holes are not just a single answer to a single question. They have emerged as one of the most versatile and powerful ideas in all of modern cosmology, a master key capable of unlocking a dozen of the universe's deepest secrets. They could be the invisible dark matter weaving galaxies together, the ancient seeds that grew into supermassive giants, and the very reason our material universe exists at all. They might be hiding as Planet 9, dying in flashes of radio waves, or preserving the information of every particle they have ever consumed. Their potential discovery would be more than just finding a new type of object. It would be a paradigm shift, forcing us to rewrite the story of the cosmos from its very first note to its present structure. So we turn the question over to you. After this journey through cosmic shadows and quantum echoes, which of these theories completely rewired your brain? Was it the idea that they created all matter, or that one might be lurking in our outer solar system right now? Share your mind-blown moment in the comments below, and for more deep dives into the cosmos's greatest mysteries, be sure to subscribe and hit the bell.